You're not going to hurt us, are you?
I'll try not to. All right. Good morning, everyone, and thanks for coming. It's a real pleasure to present today. So I'd like to start off with a quote by John Dewey, who said that every great advance in science has issued from a new audacity of imagination. And what that means to me is that to make radical progress in science, you must be prepared to step outside of the norm, investigate new areas, and duck under the caution tape, step into the construction site where we'll build the ideas that lay the foundation for the future. So the title is Infinity Spin, a novel way to assess musculoskeletal symmetry. And as you probably realize, this is a bit outside of the scope of the typical ChemAt project. So what actually is the infinity spin? And no, it's not some crazy roller coaster ride, as it might sound like. But in fact, it's just a simple motion pattern performed with a star that looks like this. And it originates from the art of fire dancing. Now, what is symmetry, and why is it measured? Well, for this purpose, I've defined symmetry to be something that's equivalent when mirrored about one axis, or plane. And it's important in quite a few areas. For example, one of them being sports, running and swimming, which both have symmetrical properties. Symmetry analysis, therefore, is prominent in gait research, like walking and running. But these, thank you, Brent, these gait research and these studies, they're usually quite time intensive and require expensive equipment to do. And they also only measure data in one dimension, like this, not this way and this way. So for this reason, I've wanted to see if we can do some sort of symmetry analysis just using some simple equipment and not too much time. So this led me to defining my research objectives, which you can see here. Put simply, it's what should we measure, how should we measure it, then actually measuring it, and finally determining the actual viability of using these initial measurement units to assess musculoskeletal symmetry. So what were the main components of this methodology and how was the research actually performed? Well, the components were threefold. So firstly, there was motion capture, which measured position through the use of infrared cameras that would pick up highly reflective markers on the star, some of which are marked here, and there was another one here. This would be done at 100 hertz. Next, there was electromyography, which, as Nubel mentioned, measures muscle activation through the use of electrodes, and this was done on 6 key muscles bilaterally. Then there were these inertial measurement units that you've had a look at. They're quite small, compact. They measure acceleration. That's what they do, and they do that at 1,000 hertz. So as you can see here, these are the muscles that were measured and the numbers correlating to the specific muscles, and that was on either side as well. So there were 5 main components, stages to my experimental procedure. The first being the subject completing a questionnaire just to ensure that they were eligible for the study. Then there was the setup, the experimental setup, which was calibrating the system, the equipment, and preparing the subject. Then there was the maximum voluntary contraction stage. This is where the subject would tense their muscles as much as possible to get 100% activation as a reference, so that later on when we're measuring muscle activation, we can see what is this as a percentage of the maximum activation. Then there was the actual spinning motion performed, where we would record data for 30 seconds per trial. And then the data was filtered. I used a low pass filter at 1 hertz because the frequency is quite low, just to filter out most of the noise. And then it was processed and analyzed. What data was actually obtained and how can we interpret this data? Well, if you have a look here, there's a nice visualization of the whole trial of this motion spin pattern, right? And the color indicates the intensity of muscle activation for this instance, particularly the trap for the right side. So you might be thinking, okay, well, what does the left side look like? Here you go. You can see that there is some symmetry observed between the right and the left sides. So it's interesting, to what extent does the symmetry actually occur? How do we measure it? Well, if we take this one cycle, right, we call this 0%, goes through to 50, and 100%. We say that's one cycle. We put all of that data into one graph. So through from 0 to 100%, and you overlay that, all of the cycles within one trial, into X, Y, and Z dimensions. This indicates the position, with the black line being the average and the blue lines representing 2 standard deviations. So we can similarly do that for the electromyography. So clearly you can see there are some patterns for certain points of the cycle correlating to certain muscle activations. And we can also do that for the inertial measurement units. So we can definitely see there is some consistency in terms of when certain things occur throughout the pattern. But how does all this relate to symmetry, you might be thinking? Well, we can use 2 major symmetry metrics. The symmetry index and the percentage overlap. The symmetry index indicating a high value being less symmetry, and the percentage overlap is kind of just symmetry, with the higher value being the greater the symmetry. Now here, if we take the left-hand side data, the interpolated stuff for the whole trial, and we take the right-hand side data, which is indicated in red, and we put those 2 graphs onto each other, we can visually see how symmetric the patterns are in the X, Y, and Z dimensions. Now, I'd just like to point out here at the bottom, on the right-hand side, the percentage overlap of the 2 motion capture position data is almost 100%, with only 5.2% of position data in the X dimension being statistically significant as an asymmetry. So we can also do that for EMG, so there's a lot of colorful graphs there. And you can see as well, I'd just like to point out the main one where the bicep has a percentage overlap of 16.8%. So that means that the rest of that, up to 100%, is statistically significant asymmetry. So clearly there is some asymmetry that can be measured through electromyography. Now if we do this with the inertial measurement units, we also see that there's a 92% of overlap of the symmetry. And this does indicate a high level of symmetry, which isn't really in line with what the electromyographic data shows. So it indicates that it might not be ideal as a use of actually diagnosing symmetry. So what conclusions can we actually draw from this data? Well, firstly, we can determine that the position and the acceleration data aren't really reliably indicative of asymmetry. The muscle activation data is the best indicator of muscular asymmetries in this motion pattern. And that, thirdly, the musculoskeletal symmetry is actually present, so we can actually measure that. And primarily, this is found to be in the bicep. Finally, we can conclude, based on the first conclusion, that accelerometry can't actually be used as a standalone symmetry assessment technique, or at least not as accurately as some of the other techniques. So what could actually be improved, and what else could be done in the future? This was an indicative study and very preliminary analysis, the first of its kind. So there is quite a lot of space for future work. Firstly, is the forearm a better indicator of symmetry measurements? When doing this pattern, there is quite a lot of strain that occurs in the forearm. The reason why it wasn't included is due to complexity. The forearm muscles are very complex. What is the actual cause of the observed variability? We know that it exists. What actually causes it would be interesting to find out. Can this actually be used as a rehabilitation or intervention technique, where I have asymmetries and I train using this pattern? Can I actually rehabilitate myself to have a higher level of symmetry over time? There's also things like what kind of things can we draw from having muscular asymmetries already present in the subject beforehand? How does that influence it? And other variables like age and experience. So I hope that today I've given you some sort of curiosity or insight into how we can think about science in new ways. And I would like to leave you with a quote, I guess, from a name I don't think I need to mention, to infinity and beyond. Thanks.
Okay, Buzz. In terms of your analysis,
yes.
You did sort of time and position analysis. Have you thought about doing spectral analysis?
What would that be?
So
Spectral analysis.
Looking at the frequencies. So you've got these rather lovely sine waves. Have you thought about frequency change or shift with different
Interesting. Okay, so in terms of spectral analysis, I'll just go back some slides. That is something that I did kind of consider. However, the frequencies are slightly different for example, for motion capture versus electromyography and particularly accelerometry. Here you can see there's more kind of, it's kind of double the frequency or something. It is something I considered. I didn't know if it would be, how useful it would be as a metric, because this was more looking at kind of overlap of the actual position of the staff as opposed to kind of like the repeatability in the time, I guess you could say. Yeah. Does that answer your question?
Sure.
Cool. Yeah. Oh, sorry.
Rob? Does the skill of the person performing the test influence the results?
This would be an interesting thing for future
so
study.
presumably more training is more symmetry, or is that not true?
I think so.
So have you done yourself with this? And
yes.
So how do you compare versus the
Probably
bunnies?
better than average. I think that this would be an interesting area of further study to compare people who are experienced in this versus people that aren't. Because I do think my hypothesis would be that people who are more experienced do exhibit greater asymmetries, which is what led me to the future work idea of whether it can be used as a rehabilitation technique, because people who actually have experience in it have more symmetry. So then that shows that having more experience would increase symmetry. Yeah. But that's just an unsubstantiated hypothesis. So, yep.
If you go back to slide 17, I was just wondering, in terms of that data, that it seems like the symmetry index and the percentage overlap are indicating different things. So do you have any reasons why that would be, and if so, which metric may be more valid?
See, that's a good and really hard question. So I did think about this, and it was quite unexpected, and I didn't really know what to do with it. But I did kind of come up with a reason. So when you look at the literature, the way that the symmetry index versus the way that the percentage overlap are calculated are different. So for example, there's another metric called the symmetry ratio as well. So if you think about like 32 versus 34, there's a difference of 2. And the percentage difference is quite low. But if you think like 2 and 4, the percentage difference is like 100%, right? So I think that due to the difference in the way that these are calculated, with percentage overlap and symmetry index, that's why they're indicating different things, because of like the relative versus the absolute positions, I guess. Does that answer your question?
Yep.
One last question.
So this morning I picked up my cat on the right side, and I noticed that it's always easier to pick her up on the right side than the left side. So my question is, this infinity movement seems quite difficult. Why not something simpler to measure symmetry?
Good question. I guess that kind of is one of the foundational things of my study, like why do we do this complicated pattern? I think that the reason why I wanted to do a complicated pattern over a simple one was to see if we can make certain inferences about symmetry in certain muscles due to deviations in the motion pattern at certain points. So like, do you understand what I'm saying? Like at certain points of the pattern we have a deviation which would correspond to like an anomaly in the muscular activation. And so doing the complicated pattern would allow us to get a broader range of data which we could correlate asymmetries in or correlate deviations in. Whereas with a simple motion pattern, there's only like a very restricted scope of what kind of asymmetry you can classify.
I would argue doing something simpler first is better, and then working your way to something more.
Right.
To understand the muscle next week, like you found bicep is the most important thing. So that's just one out of how many muscles?
6.
Yeah.
Yeah.
But anyway, it's a nice study.
Thank you, everyone.
Thanks.